Hi everybody, I hope this video finds you well. In today's video, we're going to be starting into section 1.9 in your textbook, which is sort of our last general technique for looking at solving first-order differential equations. In the previous videos, we've taken a look at how to solve separable first-order differential equations, linear first-order differential equations, as well as homogeneous of degree 0 and Bernoulli differential equations through a change of variables technique. In this video, we're going to focus on one more class of first-order differential equations, which are called exact differential equations. In this first video, we're going to take a look at what it means to be an exact differential equation, a technique for solving differential equations that are exact, and a technique for identifying which types of differential equations are exact. In the follow-up video, which will be the second half of 1.9, we'll actually put together the integrating factor idea from section 1.6 about linear differential equations in combination with this exact differential equation idea. So in this video, we'll be focusing exclusively on differential equations that are indeed exact, and then in the follow-up, we'll talk about how you can modify certain differential equations that are not exact into this format. Okay. Before we get into this definition and go through sort of the theorem, the big idea and everything, this type of differential equation and this general technique for solving this type of differential equation is the one sort of moment in our class where we rely a lot on some things from multivariate calculus. We're going to be discussing some partial derivative ideas and sort of integrating with respect to several variables. So some of this stuff will be sort of directly drawn from your sort of 220 or your multivariate calculus class. So just do be aware, pretty much everything else we've been doing so far, we've been able to just get away with sort of basic single variate differentiation and integration. In this one, we are going to see some multivariate stuff just by the nature of these equations. Okay, so let's get into our definition here. So a first-order differential equation is said to be exact if, when you write it in the following form, a function of x and y plus a function of x and y times y prime equals 0. So basically you have a multivariate function of x and y plus another multivariate function of x and y times y prime. So notice that with this type of exact differential equation, something only has the potential to be exact if there are obviously no functions of the y prime. You can have a function of the dependent variable, so it's not as strict of a limitation as like you would have in a linear differential equation, but definitely no function being applied to the derivative here. All right, so if we have that sort of first order sort of format here, and then we say that it's exact if there exists a function phi of xy. You will often hear phi of xy sort of referenced as a potential function, such that the partial of phi with respect to x is equivalent to this m of xy, and the partial with respect to y of this phi function is equal to that nxy. So in other words, exact has sort of two restrictions. One is you have to actually have the differential equation in this format, and then there has to exist this potential function phi so that the partial with respect to x is equivalent to this piece and the partial with respect to y is equivalent to this piece. Okay, so this is what it means to be an exact differential equation for being a first order. Just like in all the other sort of situations, we're going to state a sort of theorem. We're going to take a little look at that if you are in this situation, if you have one of these types of differential equations, then we know how to sort of solve it, just like we've done for separable, linear, and the change of variable situations. So our theorem here says if you have a first order differential equation that is exact and you've written it into this format, m of xy plus nxy y prime equals 0, and you have that function phi of xy such that the partial with respect to x of phi is equal to m and the partial with respect to y of phi is equal to n, then the general solution to this first order differential equation is given by the family of curves phi of xy, so that potential function equals an unknown constant. And again, remember that phi is often, you'll just hear me say it over and over, potential function. And you probably have heard that term potential function back from when you were taking a multivariate calculus course. All right, so let's go ahead and prove this real quick. This proof is pretty direct. What we're going to do is we're going to say, okay, since it is exact, we can make this sort of assumption. So we have got our differential equation here, and we know it's in this format. Since we know that it's exact, and we also know there exists. So backwards e there, that thing just means there exists, just as a little bit of shorthand. So we know there exists this phi of xy such that the partial with respect to x of phi is equal to mxy, and the partial with respect to y of phi is equal to nxy. Again, we know this because this is part of the definition of being exact. Okay, so then consider phi xy equals a constant. And let's go ahead and differentiate both sides of this equation with respect to x. So we're going to do the derivative with respect to x. Phi xy equals the derivative with respect to x of c. Now notice that when I'm writing this derivative, I'm doing this derivative as a standard derivative, meaning we're taking the derivative with respect to x as the independent variable, y as the dependent variable. So the right-hand side should be very easy. Of course, it's going to be 0. It might have been a little while since you did this sort of thing from multivariate course, but when you take this derivative here of this expression, treating x as the independent and y as the dependent, you can actually use a result from multivariate calculus to write this in terms of the partial differentials. So if you do this, it's sort of similar to sort of a product rule with a chain rule. You get that partial with respect to x. So in other words, you can go through and you can differentiate treating y as a constant and then treating x as the variable. And then you can add to that going back through and doing the derivative with respect to, then you can go back and you can redo that with the derivative with respect to y, treating x as a constant. But since we're also viewing y as a function of x, then by chain rule, we also get dy dx, where this, again, is the standard derivative of y with respect to x, treating y as a single variate function of x. Now, what do we know about this? Well, by assumption, this is mxy. By assumption, this is nxy. So this becomes mxy plus nxy dy dx equals 0. And that, of course, is our differential equation. Check. So this guy here is our general solution. So in other words, what we basically proven there is if you take something of this form, then it's automatically going to satisfy our differential equation because we just showed that manually, just like you guys did at the very beginning of this class where you wanted to check if something was a solution. You took that solution, differentiated it, and then plugged it in. Here we differentiated it. We didn't even need to plug in because after differentiating, we got exactly the expression we're trying to solve. So we know that this is our general solution there. Okay, so this is all well and good. This tells you that basically under a bunch of assumptions, namely assumption number 1, that you have an exact differential equation, and assumption number 2, you know what that potential function phi of xy is, then you automatically know what the general solution is. So there should be sort of 2 natural follow-up questions here. One is, how do we recognize if something is exact? In other words, how do we know when this potential function is going to exist? And then 2, how do we actually figure out what that potential function is? Well, it turns out that the answer to being able to deduce whether or not something is exact is very easy. There's what we call the check for exactness, which we're going to talk about in just a moment. And in terms of actually determining what the phi of xy is, once we get into our couple computational examples, we'll see that it's based on integrating these functions with this information that this mxy is the derivative with respect to x, and the nxy is the derivative with respect to y. So let's first talk about how you figure out if something even is exact. So this is often referenced as the check for exactness. So the check for exactness says this: suppose you have a first order differential equation and you've written it into this format. Okay, so you've written it into the format that an exact differential equation is supposed to be in. Now, of course, just because you write it in that format does not mean that it is exact, doesn't mean that there is a potential function, but you can check that it's exact by confirming the following. So we can say then this differential equation is exact if and only if the partial with respect to y of this component is equal to the partial with respect to x of this component. Sometimes you'll see this written without the partial derivative notation, written with the subscript thing. You might see this as m sub y equals n sub x. And if you guys remember from like a multivariate course, when you see that subscript of y or subscript of x, it just means we're taking the derivative with respect to y there, the derivative with respect to x there. So in other words, it basically says that you can check if a differential equation is exact by taking the partial with respect to y of this piece, partial with respect to x of this piece, and if those two things are equivalent, then it's guaranteed to be exact. It says a little bit more as well. It also says that if these two things are not equal, then you automatically know it's not exact. All right. The proof of this check for exactness is fully written up in your textbook. We're not going to go through that full proof in this video for a couple reasons. One is that it basically is just a sort of constructive proof. In other words, we just sort of manually show that this is actually true. And I don't think it's the most illustrative proof to go through. It's also not going to be a proof that we're going to spend too much time working on, because actually every computational example basically goes through and redoes the calculation necessary in the proof. So you guys are going to get plenty of practice with that sort of logic as we do our examples anyway. There is one thing that I'd sort of like to point out. I'm not going to call this a proof. It's more of just like an explanation or, sort of way to think about why this statement makes sense in case you don't want to take the time to go through that full proof in your textbook. This whole thing sort of hinges on an idea from multivariate calculus. You guys might remember that when you're doing multivariate calculus and you're talking about partial derivatives, there's a concept called the mixed second order partial derivatives. You can basically take a derivative with respect to y and then another one with respect to x, or take one with respect to x and then take one with respect to y. Those are what we call the mixed second order partials. There's a result from multivariate calculus that says if those things are continuous, then they're guaranteed to be equal. So in other words, for any sort of multivariate function, fxy is equal to fyx. Well, that sort of explains where this check is coming from. If we're sort of assuming that there is a potential function out there, then we're saying that the partial with respect to x is supposed to be m, and then the partial with respect to y is supposed to be m. So if we differentiate this one with respect to y and this one with respect to x, then we would get those mixed second order partials. And since we know that those are supposed to be equal, if we can check that they're equal, then sort of we can reverse that logic and say that, well, therefore it must have been exact. Now, the proof goes into a little bit more detail about exactly why that logic is reversible, and they show you sort of in a constructive approach. Feel free to read through it, but we're going to actually see that proof in action computationally as we do our examples, so I wouldn't worry too much about it unless you're sort of interested in it. The big takeaway from this check for exactness, though, is that if you suspect a differential equation is exact, all you need to do is write it into this format and then check these two partials are equal. If they are, you know it's exact and you can proceed to find the potential function. If they're not equal to each other, then it's not exact and you'll have to think of another way to approach it. All right, let's get into some examples using this check for exactness and also finding out how to actually determine that potential function. All right, so we're going to try to find all solutions to this differential equation. Now, before we get into doing this, again, obviously, because we're in section 1.9 and we're introducing you guys to the concept of an exact differential equation, this one will be exact. But let's think about why some of the other things we've talked about really wouldn't sort of make sense here. All right, first thing we talked about, separable. Not a lot of hope for being separable, though, because we've got multiple terms, and there's not going to really be any way to factor to separate the x's and y's. Linear. Not even close, right? We have y to the fourth and y cubed, and we have a term that involves y and the derivative of y. No hope for it being linear. What about homogeneous of degree 0? Well, potentially. I mean, this stuff looks good here. We've got some multivariate polynomials, degree 6, but then we have cosine of x. It's not cosine of y over x, so it would be very hard to think about this as a function of y over x. So, not homogeneous of degree 0. What about Bernoulli? We know Bernoulli is good when we see these powers of y, but unfortunately notice we have two different powers of y. We have y to the fourth and y cubed. And sort of even worse than that, you don't have it in this sort of Bernoulli sort of format. We have this y cubed and y together. Now, could we maybe get it into Bernoulli? Well, if you want, you might be able to play around with this one and actually make it into a Bernoulli differential equation. But it's going to be pretty messy to do that. Instead, we're going to try to do this exact approach. So what we're going to do is we're going to first write this into the format that we want. So we want to bring this cosine x over onto the other side. So 3x squared y to the fourth minus cosine x. Okay, I'm going to put some parentheses around there because that's sort of going to be this piece. And then we have our 4x cubed y prime equals 0. Okay? Now, in our sort of notation, just to sort of use a little bit of color to help you guys sort of see this, this is what we're claiming as sort of the m, and this component here, not including that y prime, is sort of being viewed as the n. So let's do our check for exactness. So what we're going to do is we're going to take the partial with respect to y. So again, this is the partial with respect to y of this. So we're treating x as a constant. Partial with respect to y here should be pretty clear. It's going to be 12x squared y cubed. And then, of course, the partial with respect to y of that is just going to be 0. So there we go. We can also do the partial with respect to x of n. So here we're going to differentiate this with respect to x, treating y as a constant. So pretty clear, we should get 12x squared y cubed. These two things here, these are equal. I don't like how that looks, so we'll just say equal. Put a little exclamation mark because we're excited. So that means it is exact. So it is guaranteed that there is a potential function out there, so that this is the partial with respect to x of that potential function, and this is the partial with respect to y. So we now know, there exists this phi of xy such that phi sub x, and again I'm just going to use the subscript notation, is equal to m, and phi sub y is equal to n. Okay. At this point, you can choose either one. It's not going to matter which you pick. You just want to start with one of these and use one of these relations to begin to solve for your potential function. So let's go ahead and use this one. Let's start with this. So let's start with phi sub x is equal to m. Well, what does this tell us? Well, we know exactly what m is. M is this expression here. So this tells us that phi sub x is supposed to be, well, our m was that 3x squared y to the fourth minus cosine x. So the partial with respect to x of our potential function is supposed to be equal to this. So how can we actually find our potential function? Well, we can integrate with respect to x. So we can say that phi is going to be the integral 3x squared y to the fourth minus cosine x dx. Now, this is an integral with respect to x, where even though we have a y in there, we're treating that now as a constant. So we're doing this multivariate integral with respect to x, so that y to the fourth is just treated as a constant. To do that, it shouldn't be too bad. Looks like we should get x cubed y to the fourth, because we integrate the x squared, make it an x cubed, divide by 3, cancels that out, and the y to the fourth is treated as a constant. And the integral of that negative cosine x is negative sine x. Now, normally, we would put plus c. But remember, we're integrating with respect to x, treating y as a constant. So what we're going to do is we're going to put plus h of y, meaning an unknown function of y, only of y. And that should make sense. If I differentiate this with respect to x, then this will give me this will give me this, and since I'm differentiating with respect to x, this will drop out entirely. So our unknown constant isn't an unknown constant, it's an unknown function of y. And that's because we chose to differentiate with, or to integrate with respect to x. So how do we figure out this h of y? Well, now we want to use the other. So now we use that the partial with respect to y is supposed to be n. So let's go ahead and do that. Let's differentiate this with respect to y and set it equal to n. So we're going to differentiate this with respect to y, treating x as a constant, so partial derivative with respect to y. So we should get 4x cubed y cubed minus cosine x plus h prime of y is going to be equal to n. What was n? Well, n was this stuff here, 4x cubed y cubed. So we get 4x cubed y cubed. Oh, I'm sorry there. This here shouldn't even be there. My apologies. We're differentiating. We're doing the partial with respect to y, so this drops out entirely. So that should just be plus h prime of y. My apologies there. And then the n, of course, was this guy here, 4x cubed y cubed. All right. So there we go. Now we can begin to solve for h prime of y. So h prime of y is actually just equal to 0. Okay? At this point, we could go ahead and integrate to do with respect to y here. So let's go ahead and do that. So we can say h of y is the integral 0 dy, which basically means that h of y is just a constant. Actually, since we wanted this to be a function of y and we're just getting a constant, that really means actually we don't need the h of y at all. It's just an unknown constant. It's not really a function of x at all. But we had to check this. So h of y, not necessary here. All right, so what does this tell us? Well, this tells us that our phi of xy is actually equivalent to x cubed y to the fourth minus sine x. And of course, if we had actually found a function of y over here, we would include that plus h of y. But in this case, we don't really need the constant. Why do we not need the constant? Well, if we go back to our theorem, our general solution is going to be setting this equal to an unknown constant. So we don't need an unknown constant in the phi of xy because, of course, we could just bring the constant over. So what this then tells us is this tells us our general solution here is going to be the set of curves x cubed y to the fourth minus sine of x equals some unknown constant. And of course, this is a different constant than what we found there. Had we included this plus c, again, you would just bring it over to the other side, redefine this constant, and you'd get the exact same thing. So there we go. There's our general solution to this exact first-order differential equation. Now, as I mentioned, the check for exactness that we didn't go through the full proof of basically explains how this process here, once we've established that the mixed partials are equivalent, is always going to work. In other words, once you know that the mixed partials match, you can go through, integrate one of the pieces with respect to one of the variables, and then use the other piece to determine the unknown function of the other variable. So if you go through and you read that formal proof, it's actually basically just doing this, but in complete generality. All right, let's go ahead and take a look at another example, taking a look again at how to run this check for exactness in solving an exact differential equation, along with also now including the IVP sort of situation. So let's go ahead and take a look at our second example. So we're going to try to find the unique solution to this IVP with y of 1 equal to 1. Notice that we're not proving that it's a unique solution, but we are being told in the problem that there is a single unique solution that we're trying to find. So we've got this crazy expression, e to the y plus x e to the y prime equals 5x to the fourth minus y prime over y. Is this going to have anything else that it could potentially be? We're not hopeful about being separable because we have so many different terms that mix x and y together. No hope that it's linear because of the e to the y. We don't see functions of y over x, so it's not homogeneous of degree 0. And it's definitely not going to be Bernoulli because of that e to the y. We don't just have y to exponents. So hopefully this thing will be exact. How do we check that? Well, you got to put it in the format. Even if it's not exact, the check for exactness only applies in that particular format. So we need to bring all this stuff over to the other side. So e to the y minus 5x to the fourth plus x e to the y prime plus y prime over y is equal to 0. So that's just bringing everything over onto one side there. Now, let's go ahead and factor this so we can see this a little bit more clearly, and I would use some parentheses. E to the y minus 5x to the fourth plus x e to the y plus 1 over y prime is equal to 0. Now, in our sort of notation, I forget what colors I was using. Yep, okay. This is what we would call the m, and this right here is what we would call the n. So let's go ahead and do our check for exactness. So check for exactness. So our my, so our partial with respect to y here. So I'm going to take the partial with respect to y of this piece. The x is treated as constant, so it's just going to drop out. We're going to get e to the y. And on this one, I'm going to have to take the partial with respect to x, so nx. So if we do that, treating the e to the y as a constant, so the derivative of x is just going to be 1, and we're going to get e to the y. And of course, the derivative of 1 over y, since we're treating y as a constant, is just going to be 0. There we go. These things are equal. So that means this thing is exact. So we know that it's exact, and we know that there exists a potential function. So there exists this phi of xy such that the partial with respect to x of phi is going to be equal to m, and the partial with respect to y of phi is going to be equal to n. Now, again, we can start with either one and then solve. let's go ahead and just do the same thing. Let's start with this one. So just for fun, we'll continue the same approach. It wouldn't matter which one you start with, but we'll start with phi sub x equals m. So that means the partial with respect to x of phi is supposed to be equal to m, which is that e to the y minus 5x to the fourth. All right, we can start to unpack this by integrating with respect to x. So phi is going to be the integral e to the y minus 5x to the fourth dx. This e to the y is being treated as a constant. So the integral of a constant is just the constant times x. So we get x e to the y minus integral of 5x to the fourth is going to be x to the fifth. And then plus a unknown constant, but really it's going to be an unknown function of y. So there we go. And we'll see if we actually need anything for that unknown function of y. All right, to find that unknown function of y, right, now we want to use that the partial with respect to y is going to be n. So I'll go ahead and just bring this over here so we have a little bit more room. So the partial with respect to y of this thing here. So x is treated as constant. Derivative of e to the y is e to the y. So we get x e to the y. Derivative of this is going to be 0. And then we get plus h prime of y. And then that's supposed to be equal to n. N is this thing here. So we get x e to the y plus 1 over y. Okay, notice we can cancel these on both sides, and we get h prime of y is 1 over y. Notice that this makes sense. We have this right-hand side is a function of y only. If for some reason on this side we had x's and y's, we've sort of messed up because this is not supposed to be a multivariate function. It's supposed to be just a function of y, and this time it is. So we can go ahead and integrate. H of y is going to be the integral of 1 over y dy, which means that h of y is going to be ln absolute value y. Again, no need to include a plus c because that's going to be in our general solution anyway. So there's our unknown function of y. We actually need one this time, and that tells us that our phi, our potential function, is x e to the y minus x to the fifth plus ln absolute value y. So there's our potential function, and that tells us that our general solution is x e to the y minus x to the fifth plus ln absolute value y equals c. But if we go back, we remember we're actually trying to find a unique solution to this IVP, so we can plug in. Of course, we'll be plugging in implicitly, but that's okay. So y of 1 equals 1. That means x is 1 and y is 1. So it looks like we should get e minus 1 plus ln absolute value 1 equals c. So it looks like c is e minus 1. So that tells us the unique solution we wanted to find was x e to the y minus x to the fifth plus ln absolute value y equals e minus 1. And there we go. For these ones that are exact, it is never going to be a good idea to try to get like an explicit solution. We're always just comfortable having our multivariate relation here and a constant on the right-hand side. If we're looking for the general solution, it's totally fine that there's just an unknown constant. If we're solving an IVP, we just find out what that unique constant should be on the right-hand side. Alrighty. So this shows you guys a couple examples of how to solve exact differential equations. We're going to do a couple more of these in the next video, but along with one extra step, which is we're going to learn how in certain situations to apply an integrating factor to basically take an equation that is not initially exact and make it exact. And then we'll be able to do this process. So even if you want a couple more examples of this process, we will have a couple more in the next video.